Good morning, all of you. So, with the last class, we are done with the kind of first module of our course, Machine Learning for Image Processing course, which we covered the image processing part. Okay, so let me ask you this question. In our image processing course, we have discussed in filtering something called convolution. We discussed it, right? So, let me just go here. Yeah, convolution we discussed. Sorry, bear with my very ugly handwriting because I'm writing it vertically and without enough space to keep my shoulder. Right. So I'm sure you would have all heard something called as CNN. Um, have you did anyone hear about CNNs? Does anyone know what CNN means? The full form of CNN.
Convolution neural network.
Very good. This is called as convolutional neural network. Okay. Now you see a convolution here and a convolution that we have learned as a part of our filtering. Do you, so the, just want to ensure that you could establish or you could correlate both. That's very important here. So by any chance, does any of you have an idea on why they are called as convolutional neural networks? Why are they
So in
called?
CNN also we make use of kernels, and we
Correct.
with the help of
Mhm.
with a kernel we apply convolution to each of the pixel.
Right, very good. So what you do is you have an image, and what you will be going to compute in CNNs is you take kernels of different size. Let it be 3 by 3, 5 by 5, 7 by 7, 9 by 9, whatever, depending on the context and the image size you will be doing it. And what you will be computing there, or rather learning there, are the weights of these kernels that would give you the best result. Say, let's say this could have weights of W1, W2, W3, W4. Okay, let's say W9. It is these 9. If you are considering a 3 by 3 kernel, you will be at the end learning these nine weights there. That's what you will be learning in this process. And why do you think now finding out these weights would help you by relating it to the image processing that we have done? Can you somehow still go one more step ahead and try to get some intuition on why this CNN works in general? By the way, after all these layers of, there will be some downsampling will be there, there is some activation function. After downsampling, again, you will be applying different layers, and then you would be carrying some features learned from there. These all features you will feed to a final layer of classification layer, okay, which we would be now classified networks would be studying now, and then it would give you a result. But the question here is, why do you think this works? Think of it in a two-stage problem for the time being. We are a little bit oversimplifying it, but that's okay. Whatever you are getting as an output of your convolution layers, that you are giving to a classifier, and then it is based on whatever you got out of these multiple convolutional layers, it is doing a classification. Okay, class A or class B. So then why do you think this approach would work? So maybe I will refine my question. Earlier, the image processing things that we have seen filters for edge detection, for example. We have CR, equivalently, I can call it as a gradient computation. Then we have also seen filters for image sharpening, correct? And and we have seen filters even before that for smoothing. These are at least 3 kinds of filters we have seen. Now what we are doing, I am giving the weights explicitly. That versus the current CNNs, I want you to make a statement there comparing the both.
So in this filtering process we give the weights on by our own, and in this CNN we try to learn the weights for the best possible kernel.
Yes. What is that best possible thing? How do we know?
Cost function will be minimized.
Correct. To the cost function, you know the ground truth there. What to expect out of classifier? You have a training data there. That cost function somehow computes how close the output you are getting with respect to the expected outcome of it, or expected whatever it is. How good with that, how with that being my output, so it has chosen certain weights, then based on that the classification is done. How good is the classification? Because I have the training data, it is from the training data. With the help of cost function, I'll figure out. So I can roughly put it with a bit of power simplification. I can say that while in your conventional processing, you are giving certain weights as a matter of pre-processing. Of course, it is not the final thing that you do to your image. On the other hand, without exactly specifying what these kernels should do, should it do smoothing? Should it do edge detection? Should it do image enhancement? Should it do denoising? Nothing we are explicitly, without explicitly mentioning that, we are letting the algorithm to evolve these weights and find out these weights. And there also, there is this convolution. And that's why you are going to see the convolution made just to find out these weights, which is common for the entire image. So now you could correlate it like you are doing a smoothing over the entire image. Okay, that could be the Gaussian kernel in that case. You are not explicitly giving it, but you are letting it know. However, what you could and what you should keep in mind is, for a given image and a set of, or for a given nature of images that you would expect, and for the nature of the output task that it has to do, if you have some domain knowledge, it's always good to do that processing and then give that as an input to your CNNs, so that the amount of learning it has to do perhaps could come down. By that, what I mean is number of layers that you have to use there, number of kernels in each layer that you are going to use, they can be brought down. And also, you might get more reliable, a robust result. So never throw away whatever conventional wisdom or knowledge about that particular domain of application, as well as the set of image quality is there with you. See how could you always leverage from that in the whole process. Nevertheless, the CNNs will give you the flexibility to do something which you don't really know what else would give you a better result, but you will let it do it by telling it, well, this is what I would get there, and now you figure it out. What would be the best way of kernels? And again, look at this downsampling. I'm sure you all know by this time at least this, there will be an encoder and a decoder. If it is a segmentation, a simple encoder is a simple downsampling. Decoder means an upsampling. This encoder is good enough for a classification problem. So you are downsampling images and then applying these filters. That means you are trying to extract features at a higher level. Okay. Since this is a course on machine learning for image processing, and then you have learned some conventional image processing things and convolution as well, and now you guys being most of you are having a background of signal processing. So what this, where from this convolution has come, that has to be clear. And then with your domain knowledge, you can also, in signal processing, you can also say that, for instance, this is a linear operation. So any operation, any non-linear operation which might give you best results might not be well handled, or it might not learn in the best way if you're using CNNs there. For example, if you have a Gaussian pepper noise, what I want to, before saying that statement, what I want to say you is that you should have some good understanding also of the image and the nature of the noise and few other things there. For example, if you have an image corrupted with salt and pepper noise, with the learning that you have seen now, you clearly know now that this is a this can be best handled with median filter. And if you are going to, you have an encode, you are doing an image segmentation problem where you have an encoder and decoder network, maybe what could give you the best results is doing a simple median filtering on your input images. There could be other types of noises also there, and then other type of features that are used for performing the segmentation, and then feeding that to CNNs is perhaps a wise thing to do, because your CNN can never learn it, if I'm not wrong. Maybe classification, maybe your activation function would bring some nonlinearity into classification, but I cannot immediately figure out or see a reason on why, uh, uh, on how, at least if not why, it could learn these or deal with this kind of nonlinear noise, whereas a simple median filtering, do that and feed it to your network, that might do a better job. So the take home message that I want to convey before I wrapping up this image processing module is that don't blindly feed images, just sometimes as a simple vector or a simple image or a 2D matrix, or if it is a 3D image, 3D matrix. See what can be done with the conventional image processing. Is there something that I could leverage from that? Because the computational complexity in terms of memory, time, and all these things are required is significantly lower there. And it's a definitive process in most of the scenarios. So you give as a first thought what image processing, at least as a pre-processing to your images, could improve your things better. So this always should be there in your mind. For example, I'll just make one point and move to the next line. For example, in your segmentation, you have reasonably good edges in your image. Then why not do, Sobel edge filtering? For sure that this is going to find edges. Why not do that and put a threshold on the edges that you are getting and get the strong edges there? And for those of you who know a bit into it, there is something called as attention guided networks are there. That means in addition to your image, feeding your image, you feed another image which is having this, as you could think of it as another channel to your grayscale image, where you feed it the information of magnitudes of these gradients. Who knows, then you could, even with a smaller network, you might get a pretty good results there, because you know what helps, and that is something you should be feeding it well. It is like you are asking it to solve a problem for which you do not know the algorithm, but if you have some prior information in your first investigation report, in your FIR that you have filed, or you are aware, you see how you could give this information to your network. Or it might be, if not the magnitude, it might have a particular orientation that you are looking at least that orientation information also you feed along with it, so that you are not leaving this also to your convolutional layers that are there. Maybe it's not, it might at the end of the day learn, but you need a very big architecture perhaps for that, and maybe for a different initialization it might not end up there in a reasonable amount of time. Convergence might have some issues. Are these points clear? Then let me do something else. So let's take a stock of where we stand right now in the big picture of machine learning for image processing. So I would a little bit further simplify the block diagram that I was initially drawing, where you have an input, you have something fed to the sensor, and from the sensor you are getting an output. So just anyway, our course is about the image processing. So images are what you get out of a camera or a sensor. So from there I will start. For example, you have an image here. Okay, And after you have an image, what you would do is you are going to generate features. So feature generation. That's what you would be doing. You get features, and those features, what would you do then? Maybe you don't want, so you cannot deal with so many features, or you just want to use the most important features. This could happen sometimes if your features are too high. So there is feature selection is there, that module is there. And after that, if you are looking at a classifier problem, there is a classifier design that you need to do. Classifier design, right? And after you design the classifier, perhaps you go to a system evaluation. That's where you look at and evaluate how good your evaluation is there. So system evaluation, for example, it could be the false positives, how many got true positives, what is the accuracy that you have got with that. Maybe assume that your accuracies were not so good. Well, something needs to be modified. So from here, your inputs could go to, for example, a classifier might be modified, then you see with that. Or can I do something with feature selection? You may go there. Then, as I said, you might also go to this feature generator. You could look at, okay, for now, assume that this image is what you are giving. You don't have image acquisition also could be one component of it. But for the in this course, at least we are not talking about how could you improve the image acquisition, right? And what did we discuss so far? Which of these modules that we have discussed so far?
Feature generation, sir.
Right, feature generation. So this you could think of what we discussed here. You could think of in two ways. For example, just a pre-processing of your images. That's what you could think of, right? That then you could consider the whole image. You are doing some, for example, here you are doing a smoothing operation we have discussed. Okay, in smoothing, all averaging, weighted averaging, or Gaussian smoothing. Of course, that's also a weighted averaging that we have seen. Then you might use some histogram based pre-processing. For example, that histogram equalization and all variants of it, adaptive histogram equalization, and then contrast limited adaptive histogram equalization. This we have discussed. And then it might be edge detection and image sharpening. Okay, edge sharpening there, for example, or image sharpening also you could call it. This we discussed. So one way you could look at it as a pre-processing, as well as you would also realize that, for example, a histogram itself could be your feature that you would use. So it is not just pre-processing, that you could see them as also feature generation. And of course, there are even more methods for feature generation, just like for pre-processing, there are many other methods. For now, all you could think of is we did something histogram based feature generation or some filtering based feature generation. That's what we have done so far. Because as I was mentioning previously, for example, you extracted edges and remain only kept those which are very strong. And that this is your another feature that you feed to your network instead of simply giving your pixels. Or you don't want to you are so we are so lazy that we don't want to do anything on our own, but some simple pre-processing you want to do. Let's say then you have applied, let's say, what, a simple Gaussian smoothing and gave it. Or else you realized that the contrast is pretty low in that region. Why not use histogram equalization? This you would see typically a good improvement in your results, particularly when you have a low contrast. Like that too, this mapping is not always linear. You already know it. Now, leaving it to your network, which is using linear operation of convolutions, versus you doing it using some nonlinear operations like intensity stretching. I have not written here. I could also have written the gamma. Okay, gamma, what is it? Gamma transformations. And what else did we discuss there? Histogram based anyway. Equalization is also a nonlinear operation. Of course, you could always argue that with activation function and all, the your CNNs can also deal with it. But let's not go into that. This is a much more elegant, definitely an elegant way, particularly when you know something about the image already. Okay, so this is what we have discussed. Now, the second module I have written is feature selection. For the time being, I could also say that this is an optional module, as sometimes if your features are something that you can handle, okay, you might not need to choose some features there. So for the next few weeks, this is what is the module that we would be focusing on. That's the classifier design. This is of interest for us for the rest of the maybe for 2-3 weeks at least. This is what we would be doing. So this is now classified design. It's in fact, in the classified design, we in fact go for at least a month from now. We will work on it. But specifically this classified design, in that a particular one that we would be discussing for next 2-3 weeks is classification based on Bayesian framework. So Bayes theorem, you might be all knowing. Bayes classifier, let me write it that way. Bayes classifier. This is what, or this is something, a probabilist which is based on the concepts of probability and statistics, that you perform the classification of two classes you're going to perform. So given these features, how does it put into few bins, of each bin representing one classes? You just look at this feature and put it into one of those bins. Okay, that is what we would be doing for the now the probability based classification, Bayesian framework based classification. So let me, based on it is referred to as Bayes decision theory. Okay, or if you classify, if you want, you could write it as from the based on similar lines to what has been mentioned in your textbook, classification based on Bayes decision theory. I would also, before I go into this, would also like to emphasize one point that if you look at the recent trends in machine learning and deep learning, the textbooks that are recently coming, also one of them I was already mentioning in our earlier classes, is probabilistic machine learning or probabilistic deep learning. If you want to use one of your architectures or a framework that you have got or a method that you have got in any practical applications, there should be some that too real-time practical applications that are critical. You always would like to have some confidence established on, well, with what confidence can this network tell me that this is the result? Now, while there was a rush so far, so many methods coming in machine learning and deep learning, where they are more, the moment you are getting a good result, a leapfrog jump of, let's say, 10% over the state of the art methods that are using conventional methods. Now your deep learning method and everything, people are embracing that so far. Now, that's, as far as research is concerned, this is good that you have seen something is working and you have come up there. But now is coming the trend. Okay, by the time you finish your BTech or MTech or PhD, whatever, and go to an industry, now it's time when people are looking at explainability of these networks, the confidence or with which you could say that this works better, right? And all these things would require you to establish such things. You should have a good background in probability. You should have, your concepts should be pretty clear. Then only you could formulate or recast already obtained solution that you might found it empirically by doing different experiments that it is doing well, but at least some intuitive kind of boundaries, okay, some confidence levels that you would like to say. With a 90% confidence, I can tell you that this classifier gives you results. You could have a 90% confidence. That means if it has done on 10 objects, it classified, out of them 9 classifications are for sure correct. These kinds of things, from a theoretical background, not just conducting experiment and seeing the results. Who knows? Quite possible that the data that you are feeding itself might be biased. So typically people would like to see a theoretical grounds. So if you want to become a good machine learning expert in this area, you cannot avoid mathematics. It's very that again, this is not very difficult. This is so intuitive. You need to be prepared for that. That's all. Then you could learn it very well. Okay, that's what we will do for this rest part of this course. So any questions on the comments I made so far? What is the input to your classifier?
Feature vector.
Right, feature vector is an input. So we assume here that the qualities of your image or your object of interest have been captured by this feature vector. It embeds, as one of you in the beginning rightly mentioned, it's a kind of embedding an image into a very compact form, but it's not an image as such. Would rather call it as a feature vector. It could be an image, need not necessarily be an image. That's all I would say there. It's a feature vector. So why do you need a class? If I have a vector, so let me take maybe some relevant example and convey my point here about this classifier. So I suppose my classification that I want to do with the students here in who are attending this course is a very sincere student, very sincere. Okay, I don't want to use a negative word here. I would call it as not so sincere. I want to characterize this. This is the classification I want to do there. This is an abstract, in a way, an abstract thing. Or if you want a medical imaging example, a benign tumor and a malignant tumor. Just any one intensity, if it is giving you, if it is having an intensity of 100 there, okay, this is a benign, this is a malignant tumor. It is not as simple as that. Other parts of your image also will have that. There are multiple things that you would look there to make that classification. Okay, so for example, I might look your attendance. How so our TAs are every day taking, in every class they are taking attendance. The attendance tells me whether he is sincere or not so sincere. Then let's say interactiveness, so asking questions in the class. Then hope I am listening to every one of you and seeing who is asking me more questions. That shows that he's thinking about it. He's attentive on what I'm saying and he's thinking. Or if even answering questions, somebody is, how good he is answering the questions. That also is one parameter I might consider. What else could be the parameters? Okay, attendance, and also maybe the time at which he is attending. Okay, my class is at 10, he is coming at 10:05. Well, 5 minutes should be okay. Maybe if he's 10:15 and attendance is taken at 10:30, the time could also matter. And then what else could be there? Submission of assignments. Submission of your assignments there. So is he skipping submission? Is he submitting it late or submitting it in time? That will tell me something. Then marks in the assignment. How much marks is he getting in that assignments? And then maybe what else could be there? For example, the report that he has to submit along with the assignment. So report, how good is how much attention did he pay to the report? Then marks, of course, in the marks in the, let's say, this midterm exam or marks in the final exam. Okay, Why I'm writing is here is, see, a single quantity alone might not help anybody to make a classification of a simple thing. Is he very sincere or not so sincere? There are so many parameters here. And they might not take a single value here. For example, maybe the marks could be in the midterm exam, okay, out of 100 marks, he might be anything around 80 to 100 might be good here. I could consider it to be a very sincere one. It's not a single value. There is not a single vector. If I get this vector of attendance, let us assume that I have converted it into 100%, okay, scaled each of these things to 100%. So if I get 80, 84, 85, 93, 99, I would put them as very sincere. I cannot do it this way. There is a distribution here. There is a statistical distribution to each parameter. This is very, very, very important. There is a statistical distribution. So this is my feature vector. Whatever I have written here is my feature vector. And this has a statistical distribution. I cannot just now what I will do, for example, in the class of 42 or 43 students, let me put 40, a convenient number. I might do this assessment for 30. So it's like, well, I am the one who is going through all these things. I would say I'll put him in a sincere, very sincere basket, or I might put it into not so sincere basket. But I do not explicitly know the exact ranges with which I am doing. Now, after I am done this for 30 students, for the rest 10, let the algorithm do it. Now what it should do, I should feed this feature vector values for the 30 students and let it learn for the remaining 10 students. So one thing you could see here is it's not a single point. There is a statistical distribution is there. So the statistical variations of the feature vectors. Statistical variations of the feature vector. This is a one important characteristic here for this feature vectors. One more important feature is there that needs to be taken care by these classifiers. That is, there could be noise in my measurements. For example, when I am taking your attendance, there could be days when, although you were present, I missed it. By mistake, I kept you an absent despite you being present. So that's a noise in my measurement. For one of those feature vector, one of those components of my feature vector, there could be a day when you do not have power at your home, right? Then what happened? It is not because you are not sincere. It is because there is no power at your home, you are absent. Again, with respect to your sincerity, when I am characterizing or when I am quantifying your sincerity, classifying you into one of these two classes, that's a noise in my measurement. It's not because you are not sincere. It's because you do not, on that particular day, there is no internet connection. Similarly, on 1 week, your people at your home are not doing well. You had to attend them. And maybe you did not submit the programming assignment. On that day, you might have submitted 1 week late. Again, that's a noise in my measurement with respect to the classes. So it is these two important things. That's why now you bring in the probability and then you would characterize also these classes on how good they are doing or what could be the error in your classification. There is the probability of error that you are there. So this is something that we would be trying to quantify as well. And you're good that you do not have a single measurement. There are multiple measurements. Your system should desired property of your system is that there are two things. First, it has to deal with the statistical variations of each element of your feature vector. doesn't have a single value there. The second, there could be a noise in the measurement of some of these elements of your feature vector. If everything is corrupted, then of course you don't expect it to regain. Okay, there is a level up to which this should give you. If somebody is having an internet connection on one problem on one day, and on the next day I made a mistake in taking his attendance. Okay, if such things are happening one after the other, if lightning strikes for all these days or all these components, obviously you would there is nothing that it could do, because this is the only signature. It's not even signature, it's the only the characterization or a progress report that your classifier is looking at. But nevertheless, for errors in some of these measurements also, it should handle them properly. Okay, right. So then let me go a little let's do a little bit more. So what we look at are, as I mentioned, the feature vector is what we would look at. For the time being, the feature vector, you could think of it as it says a vector. Okay, so I will use the term X bar for this. To say that this is a vector, I use explicitly a bar. You also make use of this. So let the elements, let me call it as X subscript 1, X subscript 2, and X subscript L. These are my L features. So this is, if you want, this is my X bar. In that I have values for X1, X2, X3, and so on till XL. This is my feature vector X bar. Okay. Now here I have two classes here, omega 1 and omega 2. In practice, I could have, let's say, you please make a note of all these things. If you then you have a fair copy of it also, so that you will remember this and understand it better. I should not keep any bar. This is not a vector class. So let me say that I have M classes to which it has to classify. Okay, in my example, I just considered not so sincere. Okay, and then I could have other classes also. Okay, so just like that, there are M classes, and in the rest of our courses, in rest of our course, we refer to them as omega 1, omega 2, and so on up to omega capital M. So the class 1, I would write it as a subscript to that. There are M classes that we would consider. Omega M is omega subscript that will give me, and my feature vector is an L dimensional vector here, and there are M classes, and the whole Bayesian framework can be summarized. What we do here can be summarized in a single statement, that it is like assigning. What is it that you will be doing here is assigning X bar to the most probable class that it belongs to, the most probable class. If you want me to summarize the entire objective of this Bayesian framework, or even it is true for the others, is I am given a feature vector. Now I should say which is the most probable class to which this feature vector belongs to. This is all I would be doing or we would be doing in this Bayesian framework. If you want me to put that in the perspective of probability now, since we have to do the math as well, so it is like you compute a probability of omega I given X bar. Pay attention here. This is a very, very important thing. So I'll put it bit more elaborately now. For each class, for a given X bar, okay, then what I will do is for each class omega, for each class omega I, okay, this where this I varies from 1 to m, what I should do is compute probability that it belongs to class omega I given this x bar. This is what you will do for a given x bar. And then what you do is assign it to omega to jth class where probability of omega I given x bar is greater than, or probability of omega j given x bar is greater than probability of omega I given x bar for all I that does not belong, that not are not equal to j. I am slowly moving into the mathematical terms here. Let me tell it in first in a very simple terms here. Given an x bar, you compute the probability given this x bar, what is the probability that it belongs to class I? This you do it from class 1 to class m. Finally, assign it to that class for which these probabilities are assumed that you are getting 0.1, 0.4, 0.3. Anyway, the sum will be 1. Okay, you that way, let's say 4 classes, 4, 3, 7, 8.2. Now what you do, this is class omega 1, omega 2, omega 3, and omega 4. We assign it to the fourth class. That I am writing here in a mathematical form. Both intuition should be there, and you should be able to correlate it with the mathematical form as well. You could see now, assign it to the jth class. That class is such that the probability of omega j given x bar, these are those probabilities, is greater than, you vary this I for all values of I which is not equal to j, then the rest of other, when you compare it with the rest, this has to be maximum. Or I could also have written you choose that value of j for which is maximum of these probabilities of j given x bar, also in some other form also I could write, but this is more common form that we would be using. So assign it to a class j such that probability of omega j given x bar is greater than probability of omega I given x bar. And now this I can take any value except this j. So that j we are fixing, you compare it with all the rest and you see that that's the maximum. This is what we will be doing for the next 2-3 weeks. This is our goal. This is computing these probabilities is all that we will be doing. Let me ask a question here. What is that probability of I given x bar? That probability has a name. Does anyone know that name?
Conditional probability.
Conditional.
Right, conditional probability. Another name is also there to this. A posteriori probability. Did you ever hear this name?
Yes, sir.
Very good. This is called as a posteriori probability. So in the so it is what you are going to do for next few weeks is that how can you compute, given a training set where you know the labels, how do you compute these a posteriori probabilities and then make an inference on to which class it belongs to. Okay.